Alright, let's take a look at question 9 from the homework set. A quadratic equation has roots alpha and beta, and we are given that alpha plus beta is negative 13 over 6, and alpha times beta equals 1. And the question asks us to find the exact value of alpha minus beta squared. So, in order to do this, it looks like it's just easiest to use a bit of algebra. We can make the observation that alpha minus beta squared is equal to alpha squared plus beta squared minus 2 times alpha times beta. And then from there, we make the observation about alpha squared and beta squared. That one connects to our alpha plus beta and alpha times beta values in the following way. Alpha squared, well, let's write it like this first. Alpha plus beta squared is equal to alpha squared plus beta squared plus 2 times alpha beta, which tells us that alpha squared plus beta squared is equal to alpha plus beta squared minus 2 times alpha beta. And then from there everything is just nice and easy. Substituting back in, we get alpha minus beta squared is equal to alpha plus beta squared minus 4 times alpha beta. And then, well, alpha plus beta is negative 13 over 6, so negative 13 over 6 squared minus 4 times alpha beta, so minus 4. And then sticking that into the calculator, we get positive 25 over 36. Okay, let's check out question 10. The roots of the quadratic equation x squared minus xx plus 13 equals 0 are alpha and beta. It says find the values of alpha plus beta and alpha times beta. Using our same formula as before, we know that alpha plus beta is equal to negative 6 over 1, so that would be positive 6, and alpha times beta is equal to positive 13 over 1, so that would be 13. And then for part B, it says find the exact value of alpha squared minus beta times beta squared minus alpha. No problem. Expanding that out, we get alpha squared beta squared, and then it's minus beta cubed, and then minus alpha cubed, and then we've also got plus alpha beta. So writing that nicely, alpha beta squared plus alpha beta, and we got minus alpha cubed plus beta cubed. So that looks like a problem. Oh, by the way, I know this is it seems a bit over the top doing it this way because we can easily just find alpha and beta, but this section is just about getting used to the algebra. When we do this stuff for harder, well, polynomials of degree 3 and degree 4, it's not going to be so easy to find alpha and beta immediately, but you're still going to make use of the same algebra tricks. So this section is just about getting used to that. Anyway, continuing on, we need a way to find alpha cubed plus beta cubed. And a common theme in this section is actually just to consider alpha plus beta cubed. We know that's going to be alpha cubed plus beta cubed plus, and then using binomial expansion, it's going to be 3 alpha squared beta plus 3 alpha beta squared. So it's equal to alpha cubed plus beta cubed plus 3, and then it's alpha squared beta plus beta squared alpha. But if you stare at this for a couple of seconds, you can see that they both have a common factor of alpha beta. So we can actually factor out alpha beta from there. And then it's just going to be alpha plus beta in the brackets. And so all of this stuff we already know. So we know alpha plus beta is 6. So we've got 6 cubed is equal to the thing we're looking for, alpha cubed plus beta cubed, plus 3 times 13 times, and then again it's alpha plus beta, so times 6. And from that, we should get that alpha cubed plus beta cubed is equal to negative 18. And then we're ready to answer the question, because alpha squared minus beta times beta squared minus alpha is equal to this thing here, which is equal to this thing here. And so alpha squared minus beta times beta squared minus alpha is equal to 13 squared plus 13 and then minus negative 18. And so this gives us 200. Alright, let's move on to part C now. Find the exact value of alpha plus 2 over beta plus 2 plus beta plus 2 over alpha plus 2. Again, we're supposed to do this without just calculating alpha and beta here. So getting used to the algebra tricks. And the algebra trick, we can just combine it into a single fraction. So alpha plus 2 squared plus beta plus 2 squared divided by alpha plus 2 times beta plus 2. So, well, that's going to be alpha squared plus 4 alpha plus 4 plus beta squared plus 4 beta plus 4, and the whole thing divided by alpha plus 2 times beta plus 2. So that's going to be alpha beta plus 2 times alpha plus 2 beta plus 4. Okay, rewriting this, it's going to be alpha squared plus beta squared, and then plus 4 times alpha plus beta, and then plus 8. And then this whole thing divided by alpha beta plus 2 times alpha plus beta plus 4. And we know all of these numbers except for this alpha squared plus beta squared, but we also know from earlier that that's the same as alpha plus beta squared minus 2 times alpha beta, and both of those ones we know. So the whole thing is alpha plus beta squared, so 6 squared minus 2 times alpha beta, so minus 2 times 13, plus 4 times alpha plus beta, so 4 times 6, plus 8, and the whole thing divided by alpha times beta, 13, plus 2 times 6, plus 4. And calculating that should give us 42 over 29. And while we're at it, we may as well check out question 11 real quick. Decide whether each of the following statements is always, sometimes, or never true for a quadratic equation with real coefficients and with roots alpha and beta. Part A. Alpha is not a real root if and only if beta is not a real root. Well, this is correct, because if alpha is real, well, let's say alpha is not real. If alpha is not real, then alpha equals x plus iy, and y does not equal 0. And then, since we know complex roots come in complex conjugate pairs, that implies beta is equal to x minus iy, where y does not equal 0. So beta is also not real. and vice versa. So the opposite way applies as well. So alpha is not a real root if and only if beta is not a real root. And for part B, alpha equals beta implies alpha and beta are both real. Yes, this one is also correct because it is a quadratic equation, which means it can have at most 2 roots. And, well, if alpha equals x plus iy, then we also know that beta is equal to x minus iy, and if alpha equals beta, the only way that can be true is if y equals negative y, so that means that y equals 0. So that would mean that alpha and beta are both real. Okay, part C. Alpha plus beta greater than 0 implies either alpha or beta or both must be real positive values. Well, this greater than 0 thing here, this inequality, it only really makes sense if we're talking about real numbers. Is 5 plus I less than 6 minus 10i? We could only really work it out in terms of positive. Well, we could only work out which number is bigger than the other if we take the modulus of complex numbers. And since we don't have modulus in this question, we must be talking about real numbers. And the second thing to realize is so alpha and beta are real numbers, if alpha plus beta is bigger than 0, then yes, we need at least 1 to be bigger than 0. At least one of them is bigger than 0, because if they're both negative, then when we add them together, of course, we're going to get something less than 0. Or if you have one of them equal to 0 and one of them negative, you're going to get something less than 0. So yeah, we need at least one of them bigger than 0. So this one was true. And lastly, for part D, we got alpha plus beta squared equals 9 if and only if alpha squared plus beta squared equals 9 minus alpha beta. Wrong. As we've already seen, alpha plus beta squared minus 2 times alpha beta is equal to alpha squared plus beta squared. Well, I guess we could say it is sometimes true, and it is true when we have negative 2 alpha beta. So true if negative 2 alpha beta is equal to negative alpha beta, which would imply alpha beta equals 0. So we have either alpha equals 0 or beta equals 0. So in that situation, I guess it would be true. But yeah. Okay, so that's all for this video. See you later.